Hey guys, welcome back to Quantum Mechanics 2. Hope everybody had a good weekend and enjoyed the President's Day. Um, that's the one thing I like about being up north is that there are a lot more holidays than in the South. But anyways, uh, so I think I've gotten everybody's homework, and I promise that this weekend, I'll get both homework 1 and 2 graded and get them back to you. Okay, so you can get some feedback on how you're doing. And I'll start to look at maybe putting a new homework assignment out there in the Dropbox. Um, last time I started out by kind of giving you this, I can't remember what they're called, flow chart on how to, approach perturbation theory, at least, whether or not to use non-degenerate or degenerate perturbation theory. And then we studied a couple of examples of degenerate cases. So we talked about a particle in a 3D box, right, which has a threefold degeneracy, and then we introduced this perturbation in only a quarter of the box. And what we saw was that the energy corrections were, a fourth of the energy that we put in. So we, felt like we were on the right track. So that was the ground state, which is non-degenerate, and any of the excited states are degenerate. They all have three. Well, not all, but many of them have a threefold degeneracy. And so we had to apply the degenerate perturbation theory to compute the energy corrections and the new unperturbed eigenstates. Right. So we started out with our wave functions. We constructed the Hamiltonian matrix, so this really the submatrix of this the degenerate space, right? And then went about computing the matrix elements, and we found that we had 5 non-zero ones, and so we went about solving the secular equation, right? And we found that the new energy or the energy shifts were all given by this, where kappa is just some numeric constant. And then we found that we could that the eigenstates that diagonalize that Hamiltonian were mixtures. So the 1-2-1 state and the 2-1-1 state both are mixed, right? And that's because we introduced the perturbation in the XY part where we didn't change anything in the Z direction. So the 1-1-2 state, which is the excited state, I guess, in the Z direction was unaffected. Right, and then we started talking about a hydrogen atom and an external electric field, and this led us to the linear Stark effect. I don't want to have to go through all this stuff again. So the ground state was non-degenerate, so we could use non-degenerate perturbation theory, and we'd actually done that a week or two ago and found that the energy correction there goes like the electric field squared, right? That's why it's called the quadratic Stark effect. Whereas in the first excited state, there's a high level of degeneracy, okay? And one of the homework problems that I like to assign is computing this thing, the linear Stark effect for the second excited state, okay? And so that means you're going to have this gigantic, ginormous matrix that you're going to have to deal with, okay? But just always keep in mind, these things that we did, like using the hermiticity of the Hamiltonian, and then using your selection rules and things like that, and you can get it down to a manageable subset of all those matrix elements, okay? But if you have questions, shoot them towards me. I've had all the questions, but don't get freaked out by the problem because, like I said, you can boil it down to where it's just a few lines, really. All right, so we did this for the first excited state, and we ended up finding that we have two. We didn't fully lift the degeneracy, so we have two energy corrections, and we found that two of the states remain the same, whereas the other two get mixed. Okay. And that was it. All right. So what I want to do today is kind of continue this discussion on hydrogen atoms and talk about hydrogen-like atoms. So these are atoms that can have any number of protons, but they only have one electron. Okay, so we're talking about ions, if you will. Let's see if I can make this big, and if it's okay, that's pretty cool. It's kind of big, but anyways, all right. So this is going to be the first part. So we're going to talk about fine structure today, and then next time we'll talk about the Zeeman effect. All right. So what we want to do is consider hydrogen-like atoms. So like I said, a nucleus and one electron, right? And so our unperturbed Hamiltonian is just going to be of the normal form. So we have, the p squared over 2m, and we've got the Coulomb term, right? So this p squared is for the electron. So we assume that the nucleus is much heavier and is stationary and all the normal stuff, okay? And what I want to do in this lecture is consider a couple perturbations to this Hamiltonian, real perturbations, real physical perturbations, and study their effects on the eigenenergies and the state functions, but mainly the eigenenergies. Okay. All right. So the first correction I want to consider is from relativistic mechanics. So we've always assumed that the electron in the hydrogen atom is moving at a non-relativistic speed, right? That's obviously not the case when you're talking about the scale, at which, a hydrogen atom, the size of a hydrogen atom. So the electron's, whipping around. And so special relativity is going to be important, okay? And we're going to see later on that special relativity and quantum mechanics don't really play well together. And we'll actually see an example of that today. But for now, let's just I'm getting kind of sidetracked. So let me just get back to this. Okay, so what we want to do is generalize the kinetic energy of the electron to be relativistic. So what we're saying is that the kinetic energy should be the normal p squared plus m squared minus the rest mass piece, right? And so typically what we do is we say, well, the rest mass is much larger than the momentum, right? We pull it out in front of the square root. So I have the 1 plus p squared over the m squared term. And what we want to do is normally we expand this thing, right? So we expand, we do a Taylor expansion, right, of the square root, and we end up with this stuff inside the parentheses right here. And you can see that the rest mass cancels off, right? And when you multiply this times this, you get the normal p squared over 2m, right? And then we say, oh, well, this term goes like, p squared or p to the fourth over the rest mass squared. So, it's highly negligible and we can drop it, okay? Well, what I want to do today is say, yeah, maybe it's negligible, but, let's not drop it. Let's treat it as a perturbation, okay? So our Hamiltonian, so what we're going to do is this is our normal kinetic piece, right? And we're going to treat this term as a perturbation, okay? So our Hamiltonian is going to take the normal form where we have the simple piece, right? So this will be the normal p squared kinetic term plus the potential, and our h prime here, our perturbation small Hamiltonian, is going to be this p to the fourth term, okay? And this is just what I was just saying. Okay, so what we want to do is ask ourselves, what type of perturbation theory do we want to apply? Right? Do we want to use non-degenerate or do we want to use degenerate? Okay, and the first thing, before you go off and think about the hydrogen atom levels and, their high level of degeneracy and all that stuff, just take a look at, the operator that you're given, okay? So the first thing we know is that the hydrogen atom Hamiltonian has a rotational symmetry, right? And that rotational symmetry is, linked to, the angular momentum, right? And the first thing we notice is that this, the perturbation that we're considering doesn't do anything to disturb the rotational symmetry, right, of the unperturbed Hamiltonian. So in other words, another way of saying that is that this operator that goes like p to the fourth or p squared squared commutes with the angular momentum, right? So the spherical symmetry is still intact. Okay. So what that means is that this thing, the perturbation, is already diagonal in the unperturbed basis. Okay, so that means that we have no off diagonal terms, right? So we're free to just use normal non-degenerate perturbation theory, even though these states are highly degenerate. Okay, so that means that if I want to consider computing the first order energy correction, I just need to consider this matrix element, right? And this matrix element, if I plug in what H prime is, looks like this. Okay, simple enough, right? And we could actually, take this thing, right, and write it in position space. So you'd have 4 derivatives, right? So you could go through and by brute force compute this thing. But that's a whole lot of derivatives, or as we say in the South, it'd be a whole mess of derivatives. Okay, and I don't want to have to do 4 derivatives. I wouldn't, on these the hydrogen atom wave functions. So what I would rather do is come up with an elegant way to compute this. Okay, so let's do that. All right, it'll be a lot less messy, and I'll get a lot less confused, hopefully. Okay, so let's see how this works. All right, so note that the first thing we can do is take our perturbation Hamiltonian, which is the P4 term, right? And notice that if I pull out this prefactor, this 1 over 2 mc squared, right? Then I can write what's left as P squared over 2m squared, right? But that P squared over 2m is just the normal kinetic piece, right? So I can write the normal kinetic piece as the unperturbed Hamiltonian minus the potential, right? And the potential in this case is a Coulomb, so it's plus z squared over r. Okay, so I've rewritten my perturbation Hamiltonian in terms of the unperturbed Hamiltonian and the Coulomb potential piece, and this whole thing is squared. Okay, so let me plug that in to our expression for the first order energy shift. Okay, and then square everything out. Okay, and so I get these terms with H naught, the unperturbed Hamiltonian, and those pieces I know how to evaluate. Right, I know the energy levels of the unperturbed hydrogen atoms. So these H naughts I can evaluate. Right, the things that I'm going to want to try to evaluate are these Coulomb pieces. Right, the linear piece and the Coulomb potential, and the piece that's quadratic. All right, and that's exactly what I've done here. Is I've carried out those, the operations of our unperturbed Hamiltonian. So I get this term, the E squared. I get the E term times, this matrix element for the Coulomb potential, and this guy for the Coulomb potential squared. All right. So all we need to do now, and that's again sounds simpler than it really is just to compute the expectation value of the Coulomb operator and its square. Okay. So it turns out that the first one you can compute in one line, right? And it comes from the quantum mechanical version of the virial theorem, right? Which says that the total energy is equal to 1/2 the expectation value of the potential energy, right? And that's precisely what we have here. We have the expectation value of our potential energy, so we can turn this around and say that this thing is just 2 times the energy, right, of this level, right? And so what I find is that the expectation value of this thing is just twice the unperturbed energy for the level n, right? Okay, so that's one way of computing that term linear, the linear term. But there's an even cooler way to compute this term, and it's will allow us to compute this guy, right, which is a little bit tougher. Okay, so the way it goes is like this. Okay, so let's imagine that we have a hydrogen atom, okay, and it's an unperturbed hydrogen atom, and then all of a sudden we turn on this perturbation, right, and this perturbation goes like 1 over r, okay, and some constant gamma. Okay, and this gamma is some very small number, so between 0 and 1. So, it's small, so we can safely apply perturbation theory. Okay. So in this case, what we have is that the second term in this thing, I just rewrote it from earlier, right? That this guy is just the first order correction to the energy with where gamma is set equal to ZE squared. Okay, so I'm just restating the problem, saying, okay, let me, imagine I've got this hydrogen atom. I introduce some fictitious perturbation, right? And then I notice that, oh, wait, this looks like, these two terms look the same except gamma equals ZE squared, right? Now, so that's how we would approach it in perturbation theory, okay? But at the same time, we could actually solve this problem exactly, right? And it comes from the fact that because this thing goes like 1 over r, okay, so what happens is let's go back to the original Hamiltonian here, right? So if I add in that gamma over r, I can actually combine the numerators, right? And so what it does is basically it just gives you back the hydrogen atom, but the numerator has been shifted, right? So it shifts from ZE squared to ZE squared minus gamma, okay? So that doesn't affect, the solutions of the Schrodinger equation when you plug in the potential because, these are just constants, right? So I can actually solve this thing exactly, okay? And so what we have are basically two ways of solving this problem, right? We can do it in perturbation theory, where our first order energy correction is going to, or first order energy is going to be the unperturbed energy plus the first order shift, right? And then I can actually, like I said, we can solve this thing exactly, right? And if I solve it exactly, I just write down the normal solution and just replace ZE squared with ZE squared minus gamma squared, okay, squared, and then expand in gamma, right? So gamma is a small number, so we can expand, okay? So I expand it out, I get the normal, 0th order term, and then I get a first order term in gamma, right? And it looks like this. But these two ways are equivalent. They should be equivalent to first order. And so what we can do is take these two expressions, compare them, and match the first order terms in this small coupling gamma, right? So what I find is that when I do that, I find that this guy it gives me -2, so that's coming from here, -2 En naught, right? The unperturbed energy, right? And if you go back and you look at the virial theorem, you'll see that it agrees exactly with what we had, okay? So the idea is that you, write down the Hamiltonian with some fictitious perturbation, right? Then you consider the same thing, but solve it exactly, right? And then expand and then match terms, and you're able to compute these matrix elements, okay? So we can do the same thing for the Coulomb term squared, right? In this case, we have to introduce a fictitious perturbation that goes like gamma over r squared, okay? And so what's going to happen is this gamma r squared. So again, we can apply perturbation theory to it because gamma here again is very small, right? Or we could solve it exactly. And in this case, the way we do it is we absorb this term into the centrifugal term, right? Remember the centrifugal term that comes in from the spherical kinetic energy term, right? It's like an effective potential piece, right? So what we do is we just take that piece and our gamma over r squared term, we combine them, and we just define some new quantum number L prime. And so L prime is going to have dependence on L and gamma, right? Okay, so if we do that and we follow the same procedure, and we match, so we take the exact result, we expand it around gamma, and then matched to the perturbation theory result that we would have written down, we end up finding that this matrix element we can write it in terms of the principal quantum number, the L quantum number, and the unperturbed energy, right? So that means we can finally put everything together, right? So let's just go back. So this is where we're at. Okay, so we've computed this thing in two different ways, and then we just computed this guy, right? So we can go and plug all those terms in, okay? And no, this term, okay, hold on. When I did this, I noticed there was a typo, but this was right. So let me just do, okay. All right, so we plug this stuff in, right? We see everything goes like energy squared, so we can pull that energy squared out, and this is where there's a typo, so I tried to mark those out. And we can just do some simplification. We can rewrite the unperturbed energy in terms of, the normal constants, right? Like the fine structure constant, the mass of the electron, so on and so forth, right? And what we end up with is a very simple looking expression for the first order energy shift, okay, due to the relativistic correction from the electron's motion, right? And so when you get this result, you want to ask yourself, okay, so this it's order alpha squared times the unperturbed energy. Remember, the unperturbed energy goes like alpha squared. Yeah, I think that's another typo. So the unperturbed energy goes like alpha squared, right? So this, the perturbed or the first order correction is alpha squared times that, okay? And so we want to ask yourself, does it make sense physically, right? And so you can kind of go through this hand waving argument just to convince yourself that it is, okay? And the way it goes is that, so the correction that we're considering is of order beta squared. So beta is the normal relativistic beta. So it's V over C, right? So this is the beta squared correction to the normal kinetic term. And in the semi-classical picture, or, semi-quantum picture, the electron's velocity is basic. So beta is on the order, give or take, a few factors. It's on the order of alpha, right? So what you see is that, okay, I've got a correction of order beta squared. Beta is the same order as alpha. And so it makes sense that our first order energy shift is alpha squared times the unperturbed energy. Okay? All right. Okay, so that's the kind of stuff that theorists do so we can sleep better at night. All right? Okay. All right, so the second part of today's lecture, I want to consider the spin-orbit interaction and its effects on the energy levels of the hydrogen atom or a hydrogen-like atom. Okay, so up until today, we've always I don't want to say this. We haven't neglected the motion of the electron, but we've neglected the interaction of or the interaction that arises from the motion of the electron inside the Coulomb potential. Okay, and so today we're going to put that back in. All right, because in reality we know that the electron's whipping around. It's a charged particle, so it a charged particle in motion gives off a magnetic field. Hopefully this isn't news to you guys. So what we want to do is try to study, the effects of this this magnetic field, basically. Okay, and the way it works is we have to, work in the electron's rest frame. So in the electron's rest frame, it's the proton that's moving, right? And when the proton's moving, it's also creating a magnetic field, right? And the classical expression for that magnetic field is just goes like V. The velocity of the proton in this case cross r, right, where r is the position vector. So the electron's going to feel a force from this magnetic field, right? And what we want to do now is try to account for this by adding a potential term to our Hamiltonian, right? And we're going to treat it as a perturbation. We're going to assume that it's a small effect, okay? Um, so in the lab frame, the electron experiences a lot, electric field from the Coulomb potential, so we know that, right? And because the electron's moving, or if you're in the electron's rest frame, uh, the electron's going to feel a magnetic field, right? And that magnetic field is going to be given by V cross E, right, with a minus sign thrown in, okay? And so we have an effective magnetic field that arises from the electron whipping around in the Coulomb potential, right? And the electron's going to interact with this magnetic field. And the way that it interacts is through its intrinsic magnetic moment, right? And we saw this, first days of class, right? Of quantum one, right? We talked about the Stern-Gerlach experiment, right, where the magnetic moment of the electron was interacting with this magnetic field, right? So the magnetic moment, the intrinsic magnetic moment, looks like this, right? Remember, it's proportional to the spin, right? The spin operator of the electron, right? So what we want to try to do is write down a term for the Hamiltonian, right? To represent a term in the Hamiltonian that represents this interaction, okay? And so typically what we do is kind of resort to, thinking of this thing classically, right? And writing down the classical Hamiltonian and then promote observables to operators. Okay, so that's what we'll try to do. All right. So classically, we would write that the Hamiltonian piece is proportional to mu dot b, right? And with this minus sign. Okay, so now I can do some algebra, okay, to see that this is actually a spin-orbit interaction. Okay, so I'm going to rewrite my effective magnetic field in terms of the V cross E, right? And then I'm going to do some other magic. So I'm going to rewrite mu in terms of the spin operator. Here I'm going to replace V with P over M. All right, so that gives me this P. And then here I'm going to rewrite this electric field in terms of the gradient of the Coulomb potential, and it's only in the radial direction, so that's why I have this. And it's pointed in the R direction, okay, the radial direction. All right, but then you see, oh wait, P cross R, or R cross P with a minus sign, that's the angular, the orbital angular momentum, right? And so what I have are a bunch of constants, right? A derivative on this Coulomb potential piece, which is a scalar, and the dot product between the spin and the orbital angular momentum. And so that's where the term spin orbit interaction comes from, right? It's an interaction we started out by talking about an interaction between the electron's magnetic moment and the effective magnetic field from charges moving around. And what we end up with is something that looks like a spin orbit kind of interaction, right? So I kept this question mark here, right? Because we were basically guessing, okay? And it turns out that we're not too far off. It wasn't that bad of a guess, right? But we're off by a factor of 2. Okay, we wouldn't know this in the real world unless we went off and measured the effects of the spin orbit interaction, and we would see that we were off by a factor of 2, and so we would go back to the drawing board right after we blamed the experimentalists. But we would go back to the drawing board, okay, and it turns out that the factor of 2 is kind of beyond the scope of this lecture. We're going to eventually get there when we talk about relativistic quantum mechanics and the Dirac equation. That'll be at the end of the semester. Okay. So for the time being, we're just going to put it in by hand. Okay. And we don't do this in the real world. You don't just put in fudge factors in the real world. I just gave you guys a wink. So we're just going to put it in by hand, okay? So we got the spin orbit Hamiltonian, and it looks like this, okay? Now what we want to try to do is, plug this in and treat it as a perturbation and see how it affects the energy levels of the hydrogen atom, right? So we know that the unperturbed Hamiltonian looks like this, right? And we know that when we include the spin of the electron, right, and we're trying to solve for, the eigen functions, right, that we basically have two choices, right? Whenever we have the addition, or whenever we have two angular momenta, we have a choice of which basically base kets to use, right? So the first choice is what we call the uncoupled basis, right? This is where our eigenkets would be simultaneous eigenkets of the L squared and LZ operator, as well as the S squared and SZ operator, right? So these are totally uncoupled, right? And then we also have the coupled basis, where the eigenkets are going to be, or where the kets are going to be simultaneous eigenkets of the orbital angular momentum operator, the spin orbit angular momentum operator, and then the two total angular momentum operators. Okay, so these guys are depend on both L and S, right? They're the sum. Okay, so it turns out that, and you, as is usually the case, you can work with either of these bases and you'll eventually get to the right answer. But it turns out that one of them is extra easy to work in, and one is extra hard. Okay, and you can see which one is the easy one and which one is the hard one, because if you look at this, you see that, so our operator that we're trying to compute is proportional L dot S, right? And we all know how to take the dot product, right? So does this thing, is this thing going to commute with LZ or SZ? That's right, it's not, right? This thing's not going to commute with LZ or SC, okay? So it behooves us very much to work in set number 2, right? To work in the coupled basis, right? And that's kind of a cardinal rule in perturbation theory, is that, if you're given a choice, you choose an eigenbasis where your perturbation is diagonal, right? And that's exactly what happens, because our operator commutes with all these guys, right? So it's also a good eigen value, or eigenvalue. And so that means that the simultaneous eigenkets of all these guys are going to be as eigenket of L dot S, meaning this operator is diagonal, right? So that simplifies our life a lot. Okay, so if you guys want, I can assign, doing it in the uncoupled basis for a homework problem. Just let me know. Okay. I was just kidding, because I wouldn't want to do that. All right. So in the coupled basis, I think we saw last semester that the wave functions we can write down in terms of the normal radial piece, and then these funky looking Y things, right? And you see that Y depends on J, L, and M, right? So this is the coupled basis. That's why J is appearing. These guys are called spin angular functions, right? And so they're basically proportional to the spherical harmonics, right? With some prefactors, okay? But the point is, don't get bogged down in these definitions and what these things look like. The point is that we know what the wave functions are, right? And so we can get started by computing first order energy shifts, okay? So the expectation value, right, because we're in a diagonal basis, so we don't have to worry about any off diagonal terms, looks like this, right? And we can easily split this into the radial piece, right? And the radial piece is just going to depend on the radial wave functions, and the Coulomb piece, right? And the angular piece is going to depend on the spin angular functions and the orbital angular momentum. And spin doesn't really come into play, but I'm just going to keep it attached to L just for the hell of it, okay? So this thing I'm going to evaluate later, okay? So let's just put brackets around it so we don't have to keep writing these integrals out. And what I want to do is consider this piece, the angular piece, right? So to evaluate this angular piece, we can do a little trick. So we can rewrite this L dot S. It's kind of like a cross term, right? A cross term between, if you took L plus S and then squared it, right? And L plus S is J, right? So actually, you can rewrite this L dot S term as 1/2 J squared minus L squared minus S squared. Okay, and this is a normal trick anytime you're dealing with angular momentum. I'm sure we've seen it before. Okay, so what do we have? So we have S squared, right? And these are spin angular functions, right? So they contain information about the spin of the electron. So S squared, when it hits this, is just going to give me the 3/4, right? 3/4 H bar squared, if you want. L squared, remember these are the spherical harmonics, so it's going to be the L plus 1. And J squared, it's a function of J, so it's going to be J times J plus 1, right? Or if I put in what J is, so J can either be L plus 1/2 if the electrons spin up, or L minus 1/2 if the electrons spin down. I get two possible values, right? And that's what I have here, okay? So this integral gives me these nice little simple expressions in terms of the orbital angular momentum quantum number. All right, so I can put that back together with our what is it? I wrote it down, but we can write it down for the first order energy correction, right? So we have this piece done. We just have to still do the radial piece, okay? And before we do the radial piece, this thing's called Landay's interval rule, okay? And I'll leave it to you guys to go off and look at Wikipedia and see for yourself what Landay's interval rule is. Honestly, I can't remember off the top of my head. Okay, so we want to compute this thing for the hydrogen atom, right? So we want to replace this. The C here stands for central potential. Okay, so you could actually calculate Landay's interval rule for like a Yukawa potential, right? That's also a central potential. But we want to do this for the Coulomb potential. Okay, so for the Coulomb potential, we can plug it in. We can take the derivative, and so what we really need to compute is this thing. Okay, and again, we could do it by brute force, but let's take the higher road here. Okay, so the first thing we're going to note is that the expectation value of our of a commutator between of the unperturbed Hamiltonian and some operator A, for any operator A, is going to vanish, right? Because we know that H is going to get hit on this side. From the first term, H is going to hit over here, give me the energy eigenvalue. From the second term, it's going to hit over here, and they're going to cancel each other out, okay? So that's just an obvious statement. But let's see what we can do with it, okay? So let's take our operator A, and let's say, okay, let's let A be the radial component of the momentum, all right? So P sub R, okay? And P sub R, we know, in position space is just proportional to a derivative, right, with respect to R. Okay, so obviously this guy, PR, is going to commute with the radial part of the kinetic energy, right? And so all we're really left with to compute is the commutator. We know this thing's 0, but we want to try to get some expression out of this thing, okay? So we know that this thing commutes with the radial part of the kinetic energy, and so what we're left with is this guy, right? It obviously commutes with the, yeah, right. Okay, so let's try to go about doing this, right? So P of R is, like I said, it's just a derivative with respect to R, right? So obviously the only term that's going to come about is the term where P of R is acting from the left on this stuff, right? And so that pulls down factor of 2, and I get R cubed, and from this term I get an R squared term, okay? And we know, again, that this thing is equal to 0. Okay, so now what I want to do is I want to make use of a couple things that we've already seen. So one is that this unperturbed energy level, or the energy of level n, it goes like E1 divided by n squared, and because we have hydrogen-like atoms, we multiply by z squared. Right? And I also want to make use of this expression that we got when we were working out the relativistic piece, because it's going to come in handy, right? So I have this term, remember this was like the Coulomb potential squared term when we were working out the relativistic corrections. Okay, so let's rewrite this thing, okay? And what I want to do is I want to take one of these pieces over to the other side. Okay, so that's what I've done. And then I multiplied both sides by ze squared. Okay, so you can see here, right? So this is the L term, the centrifugal term, right? I've multiplied by ze squared, 1/r cubed, okay? And then on the right-hand side, I pick up an extra factor of ze squared, okay? So now I'll make use of, where is it? It's this guy, right? Yeah, make use of this expression, right, to evaluate this right-hand side, right? So that's what this stuff is, okay? And then I can use this relationship between these two guys to write the next line, right? So that's where this next line comes from, okay? Or if I plug in, what am I doing here? I'm plugging in for E1 in terms of fine structure constant and all that other stuff, right? And then I divide through by this prefactor here, and I end up with this matrix element, right? And that's the matrix element that we set out to compute, if I can find it. Yeah, it's this matrix element right here, this expectation value. Okay, so you go back, where are we? Yep, here we are, right? And so this is exactly what we're after. We get this piece, right? And now we can put it all together finally, right? And compute the spin orbit correction, right? And so when you put it together with the angular piece that we computed, you find that it goes like alpha squared times the unperturbed energy, and it depends on not only the principal quantum number, but also the orbital angular quantum number. And its dependence on the spin is kind of hidden because the spin of the electron is a constant 1/2. Okay, so this is the spin orbit correction. It's been measured. You can, I think, if you look in Sakurai or one of the books, I can't remember, but there's a discussion as far as like experimental results. You guys know I don't waste my time with experimental results, so go look in the books or go look on Wikipedia, and you can see some real world examples of the spin orbit correction. Okay, so that does it for today. And next time, like I said, we'll study the Zeeman effect. Okay, and after that, we'll be moving on to time-dependent perturbation theory. All right. Well, let me know if you have any questions or any concerns or anything, and I'll talk to you on Friday. All right.